Okay, welcome to the 20th class meeting of the spectrally correlated random processes. Unfortunately, I have to begin with correction. So last time I talked about what is a spectrally correlated complex valued random process. And at that time, I made a serious mistake, especially when the random process is not proper, which means improper case. So as you see here, the second order stationary random process has two important characteristics in bifrequency spectrum and complementary bifrequency spectrum. However, if we have non-zero height of this impulse fence appearing in the complementary bifrequency spectrum, what does that mean? We have cross correlation between the component at f equals f1 and f equals negative f1. So not only we have correlation of the component f1 and f1, we may have spectrally correlated components. So when I drew the Venn diagram, I had to add what? Had to add this subset of proper random processes so that not only second order stationarity, but also proper second order stationarity is what? The if and only if condition for spectral uncorrelatedness. Got it? Last time I said that second order stationarity means spectrally uncorrelatedness. That was incorrect. Got it? So we need properness of the random process. So please correct that part. And today, we will continue more discussions related to the Wigner distribution function or Wigner-Weil distribution. Sometimes people call this one as Wigner spectrum. And I told you that this terminology spectrum is quite misleading, but that is one of the people say. Anyway, so before we talk in the frequency domain, let's see some time domain analysis of second order cyclostationary processes on the frequency up and down convergence. And this is also written by myself and Gemini after a lot of feedback. So here goes the kind of summary of the definition of real valued Y-sense cyclostationarity first. Since a real valued random process Y of t is real valued, there is no additional information in the complementary autocorrelation because the autocorrelation equals the complementary autocorrelation function in this case. So Y-sense cyclostationarity, that defines in terms of the mean function and the autocorrelation function is enough. And as we know that sometimes we only need mean function and autocovariance function because we have such a relation, very simple relation. Unlike this real valued Y-sense cyclostationary random process, complex Y-sense cyclostationary process, if we just replace this real valuedness into complex valuedness, have one problem because we only have definition in terms of mean function and the autocorrelation function, not in terms of complementary autocorrelation function. That's why last time I have given you this definition of second-order cyclostationarity with additional condition in terms of the complementary autocorrelation function. Got it? Of course, if we have properness or propriety guaranteed, then the Ysen stationarity and second-order stationarity becomes the same. So propriety is often just assumed in that case. We don't need to talk about complementary autocorrelation function. Now, let's think about this case. Here, the key is that x of t is complex valued. So this is complex valued cyclostationary. So second order cyclostationary. Cyclostation. Or Y-sense cyclostationary, depending on the situation. And here we have the up-converted version of it by multiplying the carrier and taking the real part. This is the most common case when our human being generates a radio wave. So we generate a real valued bandpass random process to do a lot of things. Sometimes it could be a GPS signal, it could be a radar signal, it could be a communication signal. Anyway, so here, as I have assumed, y of t is real valued and x of t is complex valued. Got it? But they have very special relation because real part of something is what? 1/2 times itself plus its conjugate. And now, we assume this signal is, just a second. Yeah, this something is still wrong. Just a second. I'm not sure whether this is the correct file or not. Okay. Just a second. Yeah, it seems that yeah, okay. Let me delete this one. So let's temporarily do not assume x of t is Y-sense cyclostationary or second order cyclostationary. Just consider x of t is complex valued. Got it? And also, we are not going to think about that. And let's focus on the autocorrelation function of the real passband random process. Got it? Now let's see what happens. So we are interested in the autocorrelation function of the real passband signal. And by using this representation, we just plug in this one to have autocorrelation function like this. So this is y of t, and this is y of s conjugate. Got it? By the way, I will rearrange the order and upload the PDF again. It seems that the Gemini little bit hallucinated in that I said that, okay, move the discussion under the assumption of Y-sense cyclostationarity to the section something, and it says, yes, I did that, and I didn't check, and it seems that still it has this assumption here. But anyway, so if we expand this multiplication, we have 4 terms. Now, y can be rewritten as the autocorrelation function and the complementary autocorrelation function and their complex conjugates. And let's focus not only on the autocorrelation and complementary autocorrelation functions, but also the exponential functions multiplied to the terms. Then we can rewrite this one like this. So real valued bandpass random process equals 1/4 of the complementary autocorrelation function times e to the j 2 pi fc. Then we have t plus s. This is quite interesting. Usually we've seen t minus s. That is here. And also, for the complex conjugate of autocorrelation, we again have t minus s. But for the complex conjugate of complementary autocorrelation, we have t plus s. Anyway, by grouping these two and that two, we can rewrite the autocorrelation function as 1/2 of the real part of the autocorrelation times e to the j 2 pi fc t minus s and complementary autocorrelation of x times e to the j 2 pi fc t plus x. Now, here goes the question. So now let's consider T cyclostationary, wide sense or second order cyclostationary. First, what if we just say X is wide sense cyclostationary without saying that it's proper or its complementary autocorrelation is something? As you see here, without talking about the complementary autocorrelation, you cannot talk about the autocorrelation function of the real bandpass signal. So from this expression, you can immediately see that not only the autocorrelation function of the complex baseband equivalent to y of t is important, but also complementary autocorrelation is important to determine this autocorrelation function of the real bandpass signal. Got it? So now you clearly see how important the complementary autocorrelation of the complex baseband signal when we, for example, generates a radio wave that can be modeled as a real bandpass random process. Got it? So that is one thing. And second one is that not only this complementary something, now let's assume that it's second order cyclostationary, which means that this term, this factor, is a function the periodic in t minus s, and this function periodic in t minus s. Right? Now the question is, what about the cyclostationarity of y of t? So let me rephrase the question. So this is not enough, and that is good to talk about whether that provides us some information about the cyclostationarity of y of t. And now question is, under the assumption that this is the periodic function with period t of t minus s, and this is periodic with period t of t minus s. Now, is this periodic with period t in t minus s? The answer is no. Why? So we replace t with t plus capital T and s with s plus capital T. Fortunately, this factor doesn't change due to the assumption. That factor does not change thanks to the assumption. And this exponent does not change because we subtract s plus capital T from t plus capital T. So t cancels, right? However, we have this factor that is very, very problematic. So when do we have the equality between the autocorrelation of y evaluated at t comma s and that evaluated at t plus capital T and s plus capital T. So this is the problematic part. And fortunately, there is a case that some carrier frequency f sub c enables this equality. And you can easily show that this is the condition. Got it? So you substitute t plus t, s plus t for t and s, and you have that part, right? So you need center frequency of the second order cyclostationary random process must be an integer multiple of 2t. 1 over 2t. Right? Otherwise, even though your complex baseband signal is second order cyclostationary, your real valued bandpass signal may not be Y-sense cyclostationary. Right? And this may confuse you a lot, and I will come back to this topic when I discuss the cyclostationarity and this up-down conversion in the frequency domain when I talk about it. Now, what if we down convert this y of t signal with apparent center frequency fc with something wrong called f0. Right? So be careful. Before, we assumed that if this x of t is second order cyclostationary, means if it is not improper, f1 and negative f1 components have correlation. Means that you have these two components, fc plus f1 and fc minus f1 correlated. So this fc means a lot. It serves as the point of symmetry in the spectral correlation, right? Now, before we down converted by using fc as the local oscillator frequency. Now suppose we have some mismatch. Means that here you have y of t, and here you down convert it, and you take the low pass filter to have x hat. Then what can you say about the second order cyclostationarity of this x hat of t, not x of t? If f0 equals fc, we already know that because we didn't use the implication. We used the if and only if conversion in the previous discussion. So definitely this x of t is second order cyclostationary. But what about this case? Ready? By the way, as I told you, you can rigorously show that if y of t, the real bandpass process is Y-sense cyclostationary with period t, then your x of t is second order cyclostationary with period t. You can show that. So it's a kind of if and only if condition. So what about this case? And here, let's assume x is second order cyclostationary. Then again, we have the problem like this. Unless this difference between f0 and f1 is an integer multiple of 1 over 2t. Our down converted signal is not second order cyclostation. So this choice of center frequency or carrier frequency is very important when you down convert the real valued random process. Okay, but probably it's not that clear in this time domain. It will be very, very clear in the frequency domain. So I believe this a lot motivates you to talk about the next one. So here, I will just talk about the frequency domain analysis very roughly using frequency shift vectorizer and properizing fresh vectorizer. So suppose you have a random process y of t that has kind of spectral symmetry, precisely speaking, spectral conjugate symmetry with respect to f sub c. What does that mean? If you have this component fc plus f1, then it's correlated with fc minus f1. And what else? We also have periodic correlation with period 1 over t. So every 1 over t, you have periodic correlation. And you also have conjugate symmetrical correlation. And that looks confusing, but we already know what can we do. So if we have x of t, then we have the linear branch, linear section, and conjugate linear section. And here, what do? You modulate by 1 over 2t, and you filter with bandwidth 1 over 2t, and you have other branches. And here also you have 0 over 2tt and filter and other things. So here in this properizing fresh vectorization, actually we already know what is the kind of point of conjugate symmetry, Fc. Otherwise, we never have this kind of properization achieved correctly. So I can't say that. Be careful, be careful. So you have kind of conjugate symmetrical correlation and also periodic correlation. But interestingly, you can choose this as the point of symmetry and also that as the point of symmetry. Am I correct? Yeah, let me just think. I believe so. Yeah. Uh, just set M over T. Just a sec. Yeah, I think so. Yeah, since these frequencies are 1 over capital T apart, you can just choose any FC plus integer multiple of 1 over T can serve as the kind of center frequency for this conversion. But I also think since this roles can be interchanged, so still you can choose this one without any problem, I believe. Yeah. Anyway, so yeah, as you see here, arbitrary choice of frequency in the down conversion local oscillator may give you a problem. Originally, second order cyclostationary process can no longer be second order cyclostationary. So very, you need to be careful. Now, let's think in the frequency domain in terms of Wigner distribution or Wigner spectrum, if you want, or Wigner Wheel distribution. First, here goes the document written in Korean, and here goes the document written in English. So last time, I introduced the Wigner distribution function as a pseudo power spectral density. So you have some relation like this. And if you integrate over T, then you have the power spectral density over, sorry, not S, W, and X. Yeah, such a relation. So the Wigner distribution or Wigner spectrum serves as is an instantaneous power spectrum, if you want. Question? No, I'm talking about the random process. So this is power spectrum. Got it? So it's defined differently. For example, for deterministic signal x of t, then what you do is that you find just the instantaneous autocorrelation kernel, and then you Fourier transform with respect to tau. And then this is defined w lowercase x t comma f. But for a random process x of t, you have expectation of random process x of t plus tau minus tau over 2, x conjugate t minus tau over 2, and you Fourier transform it. Got it? And then this is defined w capitalized x t comma f. So it's different. Okay? You have expectation. And this is assumed of finite energy. And this is a random process defined all over the T. Got it? So this S of x, x of f is the power spectral density of the random process x of t. So they are different. Got it? Now, what you are going to do is we consider up conversion and down conversion of a second order cyclostationary random process and see what's going on in the frequency domain. In order to do that, we will think about the power spectral density, Wegener spectrum, and also so-called spectral correlation density, here termed SCD, and complementary spectral correlation density. So let's see. First, as you see here, here goes the definition of the Wegener spectrum or Wegener distribution function when X is random process. And here goes the complementary Wegener distribution function in terms of the complementary autocorrelation. Got it? Last time I talked about it and looked up the literatures and found that the people already have defined this term and have used it. So we have two Wegener distribution functions. And now the question is, what is the Wegener distribution function of the up-converted real-valued bandpass random process Y in terms of these two? Got it? So you have a clear idea. Y of t is real part of X of t up-converted. By the way, let me ask you a question. Why I just ask about the Wegener distribution function of Y, not the complementary Wegener distribution? Because Y is real valued, they are the same. So we don't need to talk about complementary Wegener distribution function for the real bandpass random process Y. Got it? So this is enough for the second order or quadratic analysis of the random process X. Got it? Now the question is, how can we find this one? Actually, as you've seen in the previous PDF file, what was that? We already had autocorrelation function of the real passband signal Y as what? 1/2 of the real part of blah, blah, blah. What was that? We have the autocorrelation e to the j 2 pi fc t minus s, and the complementary autocorrelation e to the j 2 pi fc t plus s, if I remember correctly. Or you can expand these things into 2 terms each, so you have 4 terms, right? So 1/4 something. And actually, we are going to use this one. How? We just simply replace t with t plus tau over 2 and s with t minus tau over 2. And then we are going to do Fourier transform with respect to tau to obtain the Wegener distribution function of Y. And it's just a piece of cake. So let me give you the result. Okay. Where it is? Where it is? Something's wrong. Okay, it is here. Yeah, still I have some ordering problem. I will correct it. So as you see here, as I just told you, t is replaced by t plus tau over 2 and s by t minus tau over 2. Then we Fourier transform with respect to tau to have what? Again, the real bandpass random process Y's Wegener distribution consists of Wegener distribution of X and its conjugate and complementary Wegener and its conjugate. And be careful about this 4 pi fct and negative 4 pi fct. Why this occurs? Because of that t plus s term. And also, why do we have this one? We have e to the j 2 pi fc tau factor. So if it is Fourier transformed, what does that mean? In the frequency domain, in f domain, our spectrum is shifted. So interestingly, the bandpass random process has what? The Wigner distribution of x right shifted in the f direction, left shifted in the f direction, and about the time, there is modulation. Unfortunately, this can be hardly visualized. So what we do is something interesting. We consider Fourier transform this Wigner distribution with respect to t. Then, usually in the communications course, we call the paired variable as nu, and it's related with Doppler frequency. But in the literature of cyclostationary random process, they call this as cycle frequency. Got it? Not Doppler. And they love to use alpha instead of nu. Got it? So when we Fourier transform with respect to t, the paired frequency parameter is called cycle frequency and denoted by alpha. So we have some function of alpha and f, and here we call it capital S sub yy, because we are going to find the relation between this term with the power spectrum of y. Now, if we define this way, what do we have? Anybody? So this is now Fourier transformed. So you have S xx alpha f minus fc and blah, blah, blah. So that is written here. Got it? Okay, it seems that we don't have y. Okay. So, by the way, this is called the spectral correlation density, SCD. And if we deal with a complex value random process, we can define same thing, similar thing in terms of complementary Wigner distribution function. In that case, that is called complementary spectral correlation density. But since y is real, we are not talking about complementary SCD. Now, what about this complementary, the SCD, spectral correlation density of real valued bandpass process? Now, we take two axes. F and alpha. Then what about this one? You have Fc and negative Fc. And if you have the spectral correlation density of X shaped like this one, symmetric real if, then you have something here, right? And now, what about these things? Simply assume that X is improper real, so this guy is same as that one. Then what do we have in this case? Interestingly, these two terms means what? The same thing shifted in the alpha domain by 2 times Fc. So here you have 2 Fc and negative 2 Fc, something like this. So you have in the alpha versus f plane, your magnitude of SCD shows 4 kind of components. And actually, these 2 are due to the impropriety of the random process. Why? Because if the random process X is proper, what does that mean? Complementary autocorrelations are vanishing, means that complementary Wigner distribution functions vanishing, then complementary spectral correlation density vanishes. Right? So these 2 disappear if the random process is proper. Right? Now, let me give you some examples from the references. So this is figure 1 from the reference. And as you see here, this is frequency. This is cycle frequency. You can view this as Doppler frequency if you want, but it does not have the meaning of Doppler shift. So you can say that this is frequency and this is cycle frequency. And as you see here, at alpha equals 0, right? You have right shifted and left shifted versions. And this right left shift is all due to the carrier frequency Fc. And also you have what? The 2 alpha, sorry, not 2 alpha, 2 times Fc and negative 2 Fc kind of components due to the impropriety. So these 2 are due to impropriety of X of t. Got it? And now let's see another one. Here, this is a real baseband random process. So actually, Fc equals 0. What does that mean? If Fc equals 0, in this case, these 2 collapse and that 2 collapse to the origin of this alpha versus f-axis. So you have something here. And be careful. You can see small impulse fences. And these are all due to the actually cyclostationarity of this assumed random process, because this is not only real bandpass, it's kind of BPSK with symbol transmission rate 1 over t. And as you will see, this spacing is actually 1 over t0 in this case, due to the cyclostationarity. Anyway, so let's focus more on cyclostationary assumption of x of t, and let's see what's going on. And you already know, you can read it. You already know from a lot of exams or take-homes, since the cyclostationarity of x of t, that means this autocorrelation is same as the autocorrelation at t plus capital T and s plus capital T. You can say that this function of t minus s is periodic in t with capital T. But interestingly, just think about this kind of symmetric, conjugate symmetric autocorrelation kernel. And you can also show that this is periodic in t with period capital T. It's not that difficult. You can show that. Okay? So this autocorrelation function and the complementary autocorrelation function can be expanded in using Fourier series like this. You've seen something similar a lot, right? So from the periodicity of this function as a function of t, you have harmonics in T and Fourier coefficients. And this Fourier coefficient can be easily obtained by what? Just integrating and the correlation between this kernel and e to the negative j2 pi kt over capital T during one period. So this one is what? 1 over T Rxx T tau over 2 T minus tau over 2 e to the negative j2 pi kt over T dt. Got it? As a Fourier series coefficient. Now, people define the Fourier transform of this Fourier coefficient as a function of f, because tau is paired with f, is called what? By the way, this is a cyclic autocorrelation. This is named as cyclic autocorrelation function. And this is the cyclic power spectrum. So cyclic autocorrelation function and cyclic power spectral density. Similarly, you can define complementary cyclic autocorrelation function. Complementary cyclic autocorrelation function, this one, and its Fourier transform, complementary cyclic power spectral density. And now, if you Fourier transform this one with respect to tau, then what happens? You have the Wigner distribution. So you have interesting result, specialized result for the Weiss and cyclostationary random process. Ready? So your Wigner distribution for, not y, sorry about that, for x, yeah, this is not necessary then. Yeah, so yeah, a lot of parts are missing. Yeah, I thought the Gemini have written everything, but it seems not. So here we have W x T f equals sigma L S x L f e to the j 2 pi LT over T. And we have x T f tilde L complementary cyclic power spectral density for the cycle frequency T over capital T, something like this. Ready? So this part is missing. And by substituting the Fourier transform of that one, so you have if you Fourier transform Wigner distribution with respect to T, then what happens? This one becomes delta of f minus L over capital T, right? So you have and the complementary spectral correlation density. Yeah. Oh, okay. We already have it. Okay. Yeah, yes. The order is messy. Yeah, I assumed I sorted them out, but it's not yet. Anyway, so that's why you have what? You have these two things that consists of the four components of the cyclic power spectral density of Y spaced like this. Now, what do you have? So here, just a second, just a second. Let me see. Yeah, something's not correct. This should be alpha. I'm sorry. Should be alpha. Because this T is associated with alpha, the cycle frequency. So each one has impulse phases spaced by integer multiple of 1 over capital T, the fundamental cycle frequency, along the alpha axis. That's why whenever you have cyclostationarity, you have what? In this alpha direction, you have impulse phases spaced by integer multiple of 1 over T. Got it? So just taking a look at the real bandpass random processes spectral correlation density, you can identify whether there is cyclostationarity or not. And actually, this is nothing but this, nothing but, as you will see, the bi-frequency spectrum evaluated at this one here. Sorry, this is F1 and F2. So let me, yeah, there is the result, sorry. I will give you the result. Yeah, order is very, very messy. So here, you already know the bi-frequency spectrum of random process X and complementary bi-frequency spectrum, right? And if you replace F1 with F plus alpha over 2 and F2 with F minus alpha over 2 for the SCD and minus F plus alpha over 2 for complementary SCD, actually, you have the same function, except some compression or extension along the axis and possible rotation. And that part is written here, geometrical interpretation of the spectral correlation density with the bi-frequency spectrum. So you just read it. So it's not a completely new one, okay? So be careful, okay? I believe you are very confused right now, but think in this way. We, communication engineers, usually deal with real-valued bandpass random process. However, that is an up-converted version of its complex baseband equivalent, which in many cases is second-order cyclostationary. And its center frequency is 0 in this case because we have in our mind some bandpass random process. Now, that is up-converted. When we up-convert it, we are going to use carrier frequency Fc. if fc is not chosen as an integer multiple of 1 over 2t, our real bandpass random process is not, in general, y-sense cyclostationary. However, still, we can find the fundamental cycle frequency of the complex bandpass process, and also sometimes we may know the center frequency of the of conversion. For example, I've generated a BPSK random process in baseband and up-converted with some FC, which I do not tell you. But suppose I've given you the SCD. Then actually, from these informations, you can find the carrier frequency, center frequency. Ready? Because especially the improper complex cyclostationary random process has set of candidates of FC. Ready? They have special conjugate symmetry, and that cannot be arbitrarily chosen. Ready? So in this case of real baseband case, you can see that at alpha equals 0, no two kind of symmetrical spectrum, which means that, hey, it seems that f sub c is 0 here. Now, along the alpha axis, you have, for example, this spacing 1 over some t sub 0, and you may say that, it looks like the fundamental cycle frequency is 1 over t sub 0, or fundamental cycle period is capital T sub 0. Now, let's see this one. Anybody? Don't read the caption of the figure. Okay, let me hide. Ready? Anybody? What would be the possible carrier frequency of this real bandpass random process? And what would be the fundamental cycle period of its complex baseband random process if it is cyclostationary? And as you see, this is the F and this is alpha. So we will find this one as the candidate of F, and that one as candidate of 2FC. And naturally, we take from many possible candidates, we take the frequency related to this peak value, because usually we have symmetrical spectrum of the transmit pulse. So let's see. So here, carrier frequency, Fc, is chosen 3.3 over T0. So it looks like this value is 3.3 over T0. What about that? 6.6 over T0, right? And actually, it was the SCD, spectral correlation density, of the BPSK signal carrier modulated. Now, what about that one? So as you see, there is no two terms related to the complementary SCD of x of t. So by inspecting the SCD of y, you can get some information that the complex envelope x of t may be proper. Ready? Oh, by the way, this may be a kind of down-converted version. So for example, you have y over t, and So you may handle some y hat of t that is the intermediate frequency version of y of t. It could be, so be careful. Got it? Because usually carrier frequency is very, very high, and we don't know the exact center frequency before we process that real valued band process. But from spectrum analyzer, you may have an idea that, okay, the spectrum is around 3 gigahertz. Now you down convert it to 3 gigahertz, and still there could possibly be some offset. Now you handle y hat of t, and this could be as y hat of alpha f, possibly. Because carrier is very, very high relative to 1 over t sub 0 in general. So be careful, okay? This is kind of very simplified version of SCD over a real bandpass random processor under the assumption that it could be already down-converted version to intermediate frequency. Now, here goes another one. I've brought a lot of figures from the references. So what about this? You see these two components. So definitely it could be improper random process. But unlike the previous one, BPSK, we have smaller kind of pseudo power distribution along alpha axis. So impropriety is a little bit smaller than BPSK. What would be that? It is actually OQPSK. OQPSK is different from BPSK and also different from QPSK. It is different from BPSK in that it transmits QPSK symbol after staggering two BPSK signals. And it's different from QPSK in that it's improper. What about that one? This is the MSK case. MSK can be viewed as offset QPSK with pulse shaping. Now, pulse shape is kind of sine pulse or half sine pulse. And you see the similarity between these two? Got it? They are kind of cousins. Yeah. And the last one, Manchester coded BPSK. Very complicated, but you can clearly see this improper component in the SCD. By the way, what is the relation between the power spectral density of Y and this spectral correlation? Anybody? So we already know that if we integrate the Wigner distribution of Y, then we get our power spectrum. And these two are Fourier transform pair, right? So what do we have? We have this one. And this completely makes sense. See that? So actually, we have to take out the direct delta part, like, how do you say it? Anyway, so I will use this one. But anyway, so we just look at the SCD along alpha equals 0, and the spectral height of these components are related to the power spectrum. So these just do not contribute to the power spectrum at all. Got it? That's the story, I believe. Just a second. Yeah. Where is that result? somewhere. It's buried somewhere, okay? Anyway, so what I want to say is this one. In complex baseband, we have defined second-order cyclostationary random process. And it has very, very special property in that its mean, the periodic signal, is really periodic at that baseband. If you little bit change the frequency, then you don't have periodicity. It's like, see that? Suppose you have mu x periodic with period t. What if you consider mu x hat, which is slightly modulated version? Then your mean would be this one, right? And in order for this one to be periodic in t, we need f0, that is integer multiple of 1 over t, something like that, as we've seen. So this argument claim that x of t is second-order cyclostationary with non-zero mean itself imposes us a lot of constraint. In zero mean case, so mean is now discarded, still we are saying, by saying that x of t is second-order cyclostationary with zero mean and cycle period t, we assume a lot actually, because slightly shifting that one by incorrect frequency, you don't have cyclostationarity. So you may say that, hey, this is so special, but the reality is that we human beings generates kind of theoretically or implicitly in complex baseband second-order cyclostationary random process and upconvert that signal to real passband, means that actually upconvert to the plus FC and conjugate and left shift by negative FC to have real bandpass process. That's what we do in most of the radio wave related man-made signal and engineering. Got it? That's why this makes sense and this is worth to investigate. Got it? Anyway, so during the weekend, I've read a lot and found that actually one of the references in the homepage is very well written, part 3. So let me show you the homepage. Okay, I have to update the homepage with new protocol HTTPS, but I'm kind of lazy. So you go to that one. Yeah, it seems that this is not yet updated, even though I updated. Okay, let's go back. Yeah, something's wrong. Just a second. How can, yeah, so it's updated. Yeah, I did that. So this year, references, and the last one, Schreier and Schaaf's statistical signal processing on complex value data. This book has part 3, all related to the complex random process with impropriety, but they focus on actually second-order cyclostationarity. So if you read part 3, you will find a lot of things I've mentioned today and last Thursday. Got it? So yeah, this is good. So where are we? Probably, yeah. Yeah, this is already covered in the previous one, but let's see it again. So this is written earlier with different discussion with Gemini. And as you see that we're going to Wheel distribution, if it Fourier transformed with respect to t, then you have the same information as the bifrequency spectrum with axis rotated and just compressed, extended, something like that. Yeah. So you have this one. Yeah. So this is the Wigner distribution function. And you see the difference and average frequency. Same for the complementary Wigner distribution. So that is the kind of equivalent expression as that one and that one. Got it? So 45 degrees clockwise and scaled by 1 over square root t, square root 2 along the f direction, blah, blah, blah. So got it? So I believe that is most of the discussions. So you read these two, the time domain analysis, blah, 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 this document carefully. And the next one very carefully. Then you will get the messages I conveyed today. Got it? And if you want to have more information, then what? As I recommended, you go to the book by Schreier and Sharp, part 3, about random processes. Okay, it seems that that's all for the day. And I hope from this Thursday, we can go back to shift invariant subspace and Nyquist criterion and generalized Nyquist criterion, and eventually translation series representation over random process and related papers like continuous time equivalence of Welch-bound equality sequences, and where are they? Yeah, some other topics. Got it? Okay, that's all for the day.